Okay, guys, it's going to be a long lecture today. It's about selected protein functional properties. I have decided to choose solubility as shown by the probably milk here. Water holding ability as probably employed by the sausages, gelation sausages, or it is possible that when you use egg white, it's going to form gels in the cake such as this. Emulsification is important for product like sausages, burgers maybe, and foaming. If you use egg white, again it forms foam that will make the cake higher in volume, softer to eat. So we start with what we call solubility. To understand that, you have to look at these protein molecules here. You count the charges. This is negative. There's more negative charge than a positive charge. Therefore, we say that this system has net negative charge. This is likely to be away from the isoelectric points towards the alkaline region. So this kind of protein is said to be net negative charge, and they are always in a state of repulsion with one another. Therefore, the solubility is high. You go look at the bottom, similar to the top there with net negative charge. At the bottom is about net positive charge. Numbers of positive charge is higher than the negative charge, so it becomes net positive charge. Also, this system is soluble, but the one in the middle is in a condition where the pH is equal to the isoelectric points of the protein. If you count the positive charge and negative charge, they are equal, so we say there is no net charge. The solubility here is going to be very low, but because there is no repulsion, molecule A and molecule B, when they come close together, they can form all kind of non-covalent bondings. Maybe they will even separate themselves from the solution. They becoming some kind of precipitate. Okay, so you can read the text. Solubility affected by the balance of hydrophobics. We know hydrophobic groups is somewhat buried inside the molecules, and the hydrophilics is on the surface contributing to the charges. So this charge is the one playing a role in the keeping protein soluble, and we understand now at isoelectric point it is the least soluble, and as we move away from the isoelectric point, we will affect solubility differently. Okay, to illustrate, suppose you have say soya beverage here. After heated, there are going to be lots of denatured protein here, but you can drink this soya beverage. It is liquid state. You see the solubility is very high as it moves far away from the isoelectric point. But if you decide to add acid to this soya beverage, the more acid you add, they're becoming as it approaches the isoelectric point, the solubility will drop and drop. So now later it become some kind of precipitate, and if you drain the water out of that precipitate, it may turn into tofu-like products. Okay? Even that's how they make tofu anyway. This soya milk was added with glucono delta lactone, which is a kind of acidulant that can cause the protein to precipitate out of the solutions. Okay, so this again, the positive and negative charge is equal. That is a isoelectric point, and you move away from the isoelectric point towards the more acidic region. It is the opposite of the alkaline region. The positive charge exceed the negative charge. The net positive charge is the results of the charge amount. Okay, water binding or water holding, so more or less the same. This is the ability of a food to take up or hold water Okay, as we move from the this region away from the isoelectric point, we have more water binding. We have increase in the protein water interaction. You see the red dot, that is the protein, the blue dot, that is water. So in this region here, yeah, they're gonna be water is kept within products. So you can expect this product has low sanalysis, is high yield and very high juiciness. Your boss would love to sell this product because you know you can sell high yield, lots of water. Water is money. But this region here in the isoelectric point region, the protein favor to form interaction among themselves. We call this protein interaction is in favor over the protein solvent interactions. So in this region of isoelectric point region, water is easily squeezed out from the system. The sanalysis is high and yield is low. Okay, same thing with the area above the, towards the acidic region after the isoelectric point. As we move away from the isoelectric point, you will increase the water binding to the protein. Okay. I like to use tofu as a model of a gel because it's by making during preparation of tofu, it is possible to make tofu hold more water, therefore it is soft, or you can make it hard by draining the water. Of course the formulation is going to be different and the texture will be going to be different too. Okay, one of the most important physical properties, functional properties of protein is gelation. This is 3D network of protein that entraps water. So gels is a system that able to entrap water, sausages, cheese, yogurt, etc. When you entrap water, you also hold fat and other ingredients. Bread dough, comminuted, nothing to do with community. Meat products like sausages, like burgers, gelatin, tofu, I mentioned before, yogurt. Okay, so by having gel, the gel contribute to texture and eating quality. You see the the gel matrix is obtained by balancing the protein-protein interaction here. In this region of isoelectric point, the protein-protein interaction is too much. That is not good because you cannot control the amount of water inside the gel. We want the water to be inside. So even this area towards the alkaline region, it is too much protein solvent interactions. So to achieve the balance, there must be some region. This is just an example, yeah. There must be some region where a balance exists, where protein and protein solvent interaction exists in such a way that well-ordered gel matrix is obtained. Okay, so that's what we want. As food technologists, as product developers, your job is to find this balance of protein and protein solvent. This is the schematics, the illustration how a gel is formed. Not all gel form this way. This is for heat irreversible gel formation. We call this, say, globular protein gel, say egg white or soya protein. First we start with a native protein in water. You make it dissolve in water or suspended in water, and then you apply heat. As we learned from previous lectures, it's going to be denaturation. you can see there start to expose hydrophobic groups, and then as heating continues, they're going to be aggregation. This is basically molecules coming together. They're going to be some kind of forces or binding here, but it's of course non-covalence. You measure the molecular weight, it's going to be increased molecular weight. You measure the viscosity, it's going to be increased in viscosity, but this is not a gel. It is just aggregation of molecules. Leave it for longer to heat. There's going to be real gelation, i.e. we achieve the balance between the protein-protein and protein-solvent interactions. At this stage, you see aggregates starting to form the non-covalent bondings, maybe electrostatic hydrophobics. Because of this, you see the blue there. We are starting to entrap more and more water. This network is considered continuous, three-dimensional. A gel is formed. Another functional properties, very important one, is called emulsification. You know that proteins have both hydrophobics and hydrophilic groups. The hydrophobics tend to be away from the water. Hydrophilics tend to be directed toward water phase. So because of that, the protein can be excellent emulsifiers. They can situate, that's a new word today, they can situate in between oil and water phases to stabilize them. So in the ordinary system without any protein, the oil always on top, water and oil never mixes. If you force it to agitate, you will see oil droplets coming out, and then you leave it for some time, leave it for long, it will go back to the original. The oil will always be on top, water at the bottom there. Okay, then we have a new system. We introduce protein. Very likely, very quickly, the protein will be scrambling at the interface. This is the interface. As mentioned, the hydrophobic group will be there in the oil phase. Hydrophilic group will be directed towards the water phase. Give it agitation, you shake it, you agitate, or you do some kind of mechanical agitation. Then the protein will start doing its emulsification work, behave like emulsifier. It start to surround the oil droplets like so. Therefore, when you protect these oil droplets, when the oil droplets meet another oil droplets, they will not form a layer like this. Yeah, they will be protected from the rest of the oil droplets. Even though you leave it to settle after a certain time, it will remain as it is, as a stable emulsion. It will not go back to the original. Alright, so be aware of this. Cheers. Some information in order for the protein gel to form a good emulsion, you have this criteria. Number one, it should rapidly adsorb at the interface. ADSORB, adsorb, not absorb. At the interface here, so that during agitation it can form stable films surrounding the oil droplets, and then this protein here will rapidly and readily open up and orient its hydrophobics towards the oil, and hydrophilics to the water phase. Yeah, these are the criteria for good emulsion. Okay, we're going to forming, but before that, show you this egg angel food cake. These are the typical formulation, they use egg yolks. I think that's because of the content of lecithin as emulsifier, and they use lots of egg whites here. I think the egg white here is meant for as foaming, maybe a little bit of gelation agent. See the procedures for making this angel fruit cake. Somewhere here you are instructed to beat the egg whites until foamy and add cream, etc. So obviously the egg whites here is meant for as foaming agent. Yeah. So foaming, similar to emulsion, like mentioned just now. There is if the oil as regarded as the hydrophobic phase, now the air is now the hydrophobic phase. Yeah, principle and factors are the same as the emulsion. You can form foam by using injecting of gas or air, or just simple mechanical agitation, or whipping. You really whip until air is introduced into the system. So you have the proteins here, and then we whip the agitation, we whip the system. The protein will be denatured and it will quickly adsorb to the surface of the air. As adsorption, film formation, followed by air entrapment. So now with the presence of the protein as the forming agent, the protein film will protect the air from coalescence. If without this protein, this air and this air may come together and they will become big air droplets. They're going to escape from the system, therefore you're going to lose the air cell later on. Okay. So the role of the protein, it protects the air from coalescence. You save the air. So when the protein is cooked, i.e. the protein may become gel later on, this air cell will stay and you have your cake soft and high volume. Yeah. Alright, so that's the end of it. 1, 2, 3, 4, 5 different selected functional properties. There are several others functional properties, but for our purpose I think this is sufficient. Next lecture should be on lipid as food components. Okay, happy learning.